Good. Welcome, everyone. It's a pleasure to have here Siyang Li today. Thanks a lot for accepting our invitation. Siyang is a fourth-year PhD student at Johns Hopkins University, working with Prof. Adam Miras in observational cosmology. He received his Bachelor of Arts in Physics from University of California in Berkeley and his Master's of Arts in Physics from Johns Hopkins University. His current research interests involve using the tip of the giant branch and J-region Asymptotic Giant Branch to measure the Hubble constant. Today, he will present a reconnaissance with JWST of the J-region Asymptotic Giant Branch in distance-large galaxies from irregular luminosity functions to approximation of the Hubble constant. Sean, you can start please when you're ready.
Right, thanks so much for the introduction and thank you for inviting me to speak here. And so today I'll be talking about what I'm going to call a reconnaissance of the J-region Asymptotic Giant Branch in the context of using it as a standard candle, as well as provide evidence of non-uniform asymmetry in their luminosity functions and describe how we're going to approximate the Hubble constants in the context of this irregularity. Let's see. All right, and so the story here begins, of course, with the Hubble tension, which is a 5 to 6 sigma difference between indirect and direct measurements of the current expansion rate of our universe, the Hubble constant, or h-naught. And so the right-hand side, I show the compilation plot from Dr. Di Valentino's review paper back in 2021 that really shows the state of the tension. Again, you can see there's a very large difference between the indirect and direct measurements. I'm sure many of you are familiar with this, but I just wanted to point out that although I know the Cepheids get a lot of attention, the tension is really not limited to any one particular measurement. And so at the moment, the Cepheid type 1a supernova distance ladder or distance scale is the most mature method used to measure the Hubble constant. It's also the one that yields the highest precision Hubble constants. Now, when we construct an extragalactic distance ladder, we first want to calibrate the intrinsic luminosity of our standard candle, such as Cepheids in this case. We do this using geometric distances to galaxies that host Cepheids. In our case, we have 4 galaxies, which we can do this with. I'm going to call these anchor galaxies. And with the geometric distance, as well as observation of Cepheids, we can then obtain the intrinsic luminosity of the Cepheid. We can then use that information to measure distances to galaxies that host both Cepheids and type 1a supernovae, to use the Cepheid distance to calibrate the intrinsic luminosity of a supernova. We then use that information to measure distances to further galaxies in the Hubble flow to measure h-naught. And so with the Hubble tension and hints at new physics due to that discrepancy, there's also a need for intense scrutiny of our direct measurements methods. And so that leads to motivation for more high precision distance indicators that are independent to that of existing ones, such as Cepheids, to probe their systematics and also to improve the precision of the size of the tension for theory. And so I would say the next best distance indicator, aside from Cepheids, at least for the second rung of that distance ladder, would be the tip of the red giant branch, or the TRGB. And the TRGB uses the maximum luminosity reached by red giants before they transition onto the horizontal branch, and they use that as a standard candle. And this manifests as a sudden drop in the number of stars when you look at a color magnitude diagram, for instance, as shown here on the right, where the TRGB is marked with the dashed blue line. So I won't get into much detail about this plot in particular because it's about the TRGB, but I will note that the TRGB has certain drawbacks in that it is a little limited in range and that it's fainter than Cepheids, and there has been disagreements and differences in zero-point calibration and standardization over the years. In particular, the zero-point calibration or the luminosity calibration has differed on the order of 1/10 of a magnitude. And so this search for, maybe an alternative standard candle has really led to a revival of using carbon stars as standard candles. Now, this idea was first brought up in the 1980s, but there's really been a revival in the very early 2020s by a series of papers that really have developed this method, including from Rapocci, Medor, Friedman, Zagorski, Abby Lee. The work I'm going to present today is really made possible by the pioneering efforts of these works. And one advantage of carbon stars is that they are brighter than the TRGB. In fact, they can be comparable to the luminosities of Cepheids, depending on which period you look at, but essentially we can reach further with the carbon stars compared to TRGB. And so this now brings us to the J-region Asymptotic Giant Branch, or the JAGB. And the JAGB refers to this overdensity of stars, or this clump of stars, shown here in a near-infrared color magnitude diagram, labeled J. And this J region contains these carbon-rich, thermally pulsating asymptotic giant branch stars. And the idea here is that some sort of mean or mode or median or model fit magnitude of the carbon stars in this J region can serve as some sort of standard candle. Now, the argument for this is that a star has to have a mass that lies within a relatively narrow mass range, so it's about 2 to 5 solar masses, as proposed by the Medora paper, in order for the star to become a carbon star in the first place. The star is too massive, bottom burning will occur, and carbon is burned before it can reach the surface of the star. And if there's not enough mass, the third dredge-up events are too weak to bring enough carbon to the surface. So essentially, the star has to have just the right mass for it to be a carbon star and live in this J region. Now, I will note that this argument might not actually apply to all the carbon stars in the J region. In addition, there are additional considerations such as metallicity, which might change the mean magnitudes of the carbon stars, or it might change the limit imposed by the bottom burning effect. And I'll talk about that more later in this talk. And I wanted to pause here briefly just to clarify some of the terminology that I'll be using later in the talk. And so you will probably notice that I'll be using the letter J many times when describing the JGB. And so the J in the J region name originates from a simple alphabetic naming scheme. And this comes from the Weinberg-Nikolaev paper back in 2001. On the right-hand side, I'm showing the color magnitude diagram they have for the Large Magellanic Cloud, and they define several regions. And as you can see, these regions are named in the order of the alphabet. So we have the A region here, the B region, C region, D region, and so on. The J in the J region has no intended relation to the J band, which the JGB can be observed in, or the J-type carbon star. Now, in particular, in the plot I show on the bottom, I showed a spectra from a carbon star extracted in the X-Shooter Spectral Library, together with the throughput curves from some space-based filters. And the F110W filter corresponds to roughly the J band, and the F150W in red corresponds to roughly the H band. And we can see that there's absorption features covered by both the J and the H bands. And so in terms of the spectra, there's no particular preference for observing in J over H. So observationally, the JGB is measured using a single epoch, meaning we only need an observation in 2 filters, J or H to for the y-axis of this color magnitude diagram, and a color on the x-axis. And the J region can be isolated simply with color cuts. So for instance, here, what's usually done is you make a color cut, J minus K of roughly 1.4, 1.5. That excludes the oxygen-rich HGB stars from the F region. And then you can also impose a color cut at 2, and that excludes the extreme carbon stars in the K region. Now, we were able to observe the JGB in our JWST program 1685, led by Adam Rees. This program had targeted 5 different galaxies, including MGC 4258, which we have a geometric distance to, that'll act as our anchor galaxy, which we'll use to calibrate the intrinsic luminosity of the JGB. The program also observed 4 galaxies that had hosted 6 type 1a supernovae. That includes NGC 1448, 1559, 5584, and 5643. And we will be measuring the JGB and the JWST F150W and F277W filters. So the JGB, as a relatively new standard candle, does seem to be very promising, especially what's from the literature. But how standard is it? I'll be checking this. As I mentioned, there have been many methods proposed to measure the JAGB reference magnitude used as that standard candle, and this includes the mode, the mean, the median, or model fit of the magnitudes. I'll be comparing using many of these methods. And finally, I'll be measuring distances to our 4 host galaxies using the JHB method and comparing those distances to those established using Cepheid, TRGB, and Miras, all calibrated using the same anchor galaxy. So with that in mind, I want to now show the footprints for our observation. So again, we have 5 different galaxies. NGC 4258 will act as our anchor galaxy, which we'll use to calibrate the JGB. And then we have our 4 host galaxies over here. And so we perform photometry and crowning corrections via artificial star tests using the Dolphot software. We apply foreground extinction corrections using the Schlafly and Finkbeiner dust maps. So next, I want to introduce how exactly we're going to measure the JGB. And what's typically done is a box is imposed on a color magnitude diagram, and this is to isolate the J region. And so what we're going to do, we're going to use a box widths that are consistent with what's generally been used in the literature, and several standard deviations around the luminosity function or the histogram of magnitudes of stars in the J region. And this is to make sure we include all the carbon stars, as well as don't truncate the luminosity function, which might affect our statistics. Now, as I mentioned before, there have been several methods proposed to measure the JGB. Broadly, these methods seek to identify the peak of the luminosity function. So again, it's the histogram of magnitudes of our carbon stars. And this can be done different ways. So you can use the mode of a binned luminosity function after it's been smoothed. This was used by Abby Lee's paper. There's also, you can take the mean or the median. It's done by the Medor and Friedman papers. You can fit a model and use one of the model parameters as the reference magnitude. That's done by the Zagorski paper. Or you can use a modified median, including maximum likelihood statistics, for instance, and that's done in the Rapocci and Prada papers. I do want to note that the mode method does require binning of the histogram and also smoothing. And this smoothing introduces an additional parameter that you can adjust. So a higher smoothing results in more heavy smoothing, lower smoothing parameter results in less smoothing. And this will affect measurements, which I'll talk about later on. And so with all these different ways to measure the JHB, this brings us to several possibilities of constructing measurement variance. And so we sought to explore as many of these variants as we could, and then as many ways as we can measure the JHB as we could. And so we explored 25 different combinations of measurement variance. This includes 5 different color ranges, as well as 5 different summary measures. And that includes using the median, the clipped mean, the mode with 2 different smoothings, and the model fits. We did also try to look at the binning variance or changing the binning for the methods that require binning, and we found that those made very little difference. So the first thing we sought to look at was the standardization and the consistency of the JGB. And one way you can do this is looking at the variation in the JGB and how that varies field to field. Now, ideally, for a good standard candle, we would expect that the magnitude of that standard candle should not vary significantly depending on the field you look at, given it's in the same general region, such as the outer disk for the JGB or like the halo for the TRGB. And so we first looked at this in NGC 4258. And so here we have 2 different fields. We have the east field and the west field. East is on the left, and that corresponds to the B modules. And then west is on the right, and that corresponds to the A modules. And those are corresponding to the cameras on JWST. And we're going to be very thorough in doing this test. And so we're going to first introduce this inner region, which consists of the B3, B4 chips, as well as the A3, A4 chips, of course, because they're in the inner sides of those 2 modules, and then the outer regions, which contain the B1, B2 chips and the A1, A2 chips. And on the right-hand side, I'm plotting the color magnitude diagrams together with the corresponding luminosity function for the J region. Again, the luminosity function is just the histogram, the magnitudes of the stars, in this case, in the J region. And we can see immediately that all of the luminosity functions are very asymmetric. Now, we can measure this in a few different ways. We can take difference between the mode and the mean, see that that difference can be about 2/10 to 3/10 of a magnitude. We can also use the Pearson skew, and we see that's also pretty high. Now, one thing we can do qualitatively is compare this JGB magnitude to the TRGB, which would be a more mature and established standard candle. And so we can visually identify the TRGB by looking at this drop in the number of stars and the density of stars. And I show this roughly with the blue arrows. And we can see that in these 4 different color magnitude diagrams, the distance between the measured JGB and the TRGB can, differ by a little bit. For instance, it's a little, closer here, or it's a little further here on the top left. Now, another thing we can look at is how do the measured JGBs compare in this initial, the fields here. So for the outer east, for instance, we see that the measured JGB is not really consistent with the JGB measured in the outer west fields. And so I'll talk about that more in a little bit. So the first test we conducted was a symmetry or asymmetry test in the outer areas of our fields. The outer fields, again, include the B1, B2 chips and the A1, A2 chip. So what we're going to do here is we're going to measure the JGB using stars from B1, B2, and then comparing that to the JGB using stars from A1 and A2. And ideally, we would expect that for a good standard candle, your measurement shouldn't really depend significantly depending on which side of the galaxy you look at. So on the right-hand side, I show the differences of the measured JGBs, east minus west on the y-axis, and I plot that as a function of the variant numbers. So again, we have 25 different measurement variants, 5 different color ranges, as well as 5 different methods. And we can see that most of the measurement variants, they're generally clustered around maybe 2/10 of a magnitude. We would expect for a good standard candle that the difference should be consistent with 0. And that's what I show with the dashed black line here. And so because most of these measurements are actually not consistent with 0, that might be suggesting something intrinsic might be going on. Now, the next test we looked at was comparing the inner areas of our fields, of our modules. Now here, of course, we have more stars because we're closer into the disk. Again, here, what we're going to do is we're going to measure the JGB using stars from the B3 and B4 field and comparing that to the JGB measured using stars from the A3 and A4 areas. On the right-hand side, I show the same thing as before. And we see that even with more stars, most of the measurement variants are not consistent with 0. And I'd say maybe the mean would be a little less than 5/100ths of a magnitude. There is better agreements, generally closer to 0. But one thing that's interesting to note that is in this case, the model fit tends to perform the worst in terms of this symmetry test. And you can see that with the black points right here. But if we go back to the outer area tests, the model fit actually performs the best. And so that suggests that this field-to-field variation is not necessarily uniform. Now, the last thing we looked at was, what if we combine the inner and outer fields? And here we have the most stars to work with. We see that the differences are still mostly non-zero, not consistent with 0, clustered around maybe 5/100ths of a magnitude. What's interesting to point out is that a lot of the variation is not necessarily due to the color. The color range matters very little, and that's shown by the differences in the shapes, at least for most of the points. But what's causing a lot of the variation is due to the method. And that's really due to this asymmetry in the luminosity function. And I'll talk about that in a little bit. So we repeated this test using NGC 1448 and 5643. So I show 1448 here on the left, and then 5643 here on the right. In this case, we tried our best to make these to separate the fields so that there's some degree of axis of symmetry to make this comparison with. For 1448, we draw a line through the center of the galaxy and define a northwest and southeast field, plot the color magnitude diagrams and luminosity functions here on the bottom, and we can see immediately that the mode JWST at least are not consistent across the galaxy. Now for 5643, we have these two fields as shown here, north and south. What's interesting to see is that the measured mode JGBs are actually very consistent in 5643. And this kind of suggests that this field-to-field variation can be better in some galaxies compared to others. Now here are the same plots as before, where I plot the differences in the measured JGBs between the two symmetric fields as a function of the variance number. 1448 shows most of the measured variants are not consistent with 0, whereas for 5643, most of the variants are consistent with 0. So again, that suggests that there's this, the variation changes depending on the galaxy looked at. So I mentioned the effect of the differences in the measurement type. And so this primarily arises due to the irregularities in the luminosity function. And so we do find evidence of this non-uniform asymmetry in the JHB luminosity function, which inevitably causes differences between methods. So in other words, when your luminosity function or your histogram is symmetric, your mode will agree pretty well with your mean and your median. But if your luminosity function is asymmetric, your mode is going to be different from your mean and your median. And in particular, in NGC 4258, we find that the difference between the mode and the mean can be almost 3/10 of a magnitude. We do also see non-zero differences, although to a lesser extent in our supernova hosts. Now, we also look to see if this, this effect also existed in ground-based data of the Large Magellanic Cloud and the Small Magellanic Cloud. And what we did here is we took data from TUMAS and the H and J band filters, and we measured the JGBs, and we took the difference in the JGBs between these two galaxies. And in principle, for a good standard candle, that difference in the standard candle magnitude should agree very well with the difference in the geometric distances, in this case determined via detached eclipsing binaries. And so the geometric distances act as our gold standard to compare our standard candle with. And when we plot the differences, again, with all these different 25 different measurement variants, we see that not all of the measurement variants are consistent with the geometric distances. So the next thing we looked at are what we're going to call angular symmetry tests. So this uses the same principle as before. Ideally, for a good standard candle, we would expect that the magnitude of your standard candle should not really vary significantly depending on the angle you look at around a galaxy. Now, how we do this is we take our galaxy, and then we define this 90-degree window, which I'm trying to show here. We measure the JHB in this 90-degree window, and then we just simply slide that window 360 degrees. And so this is what the results look like. We looked at NGC 1559 as well as NGC 5584 on the right. For each galaxy, we also looked at 4 different measurement types when we measure the JGB, which is plotted here on the y-axis as a function of the angle, which is plotted on the x-axis. And we immediately see that there's quite a bit of variation on the order of about 1/10 of a magnitude from maximum to minimum. The yellow stars that I show here are windows that are non-overlapping, so they're uncorrelated, and we see that even with the uncorrelated points, there can be differences that are several sigma. Now, in addition, these variations still persist across methods. So we still see about 1/10 of a magnitude difference, max and min, across the mode and the mean and the median measurements. And so this suggests that there might be something intrinsic going on in the populations. So the next thing we looked at was our distances. So we measured distances to our 4 host galaxies using the JGB. And we're going to compare them to the Cepheid distances to the same galaxies as well as comparing them to TRGB and Mira distances. And so here are what the plots look like. On the y-axis for the plots on the right, showing the distance moduli, I plot that against the variant number. So again, we have 25 different variants. Now I show in the red line the median JHB measurements across all 25 of those measurement variants. And then in blue, I show the Cepheid distance from REASE 2022 adjusted to account for only one anchor, NGC 4258. Now I also show in orange the TRGB distance, as well as the Mira distance in cyan for 1559. And so in general, we do see this broad agreements with the distances, JHB distances compared to Cepheids, TRGB, Miras. But there is this methodological variation that arises due to the unequal asymmetry of the JHB luminosity function. And this causes differences in the JHB measurements that span almost 2/10 of a magnitude. And this would be the largest systematic in H0. And so because these variations are so large, we decided that we need to incorporate these variations into our H0 measurements. We find roughly 74.7 plus or minus about 3, although there is a full range spanning 71 to 78, depending on the type of measurement you choose. So you might be wondering, where does this asymmetry come from? And that would be a good question. Now, I wanted to point out that these asymmetric luminosity functions are also found in other studies. So for instance, in the Parada 2021 paper. What I'm showing here is a plot from their paper that shows the luminosity functions for the galaxies that they analyzed. And they found the luminosity function for the Large Magellanic Cloud, shown in green, as well as NGC 6822, shown in red, have asymmetric luminosity functions, whereas for the Small Magellanic Cloud, shown in orange, and IC 1613, shown in the bluish, they're very symmetric. And so this kind of supports our observations that some luminosity functions can be more asymmetric or asymmetric compared to others. Now, what the Parada paper attributes this to, and also what is talked about in the Caracas paper, is that metallicity can be the driver of this asymmetry. And so what we're looking at are different populations with different levels of metallicities that might be shifting the mean magnitudes of the JGBs. And when you have a mixed population of metallicities, that skews the luminosity function. Now, another possible explanation would be that we could be looking at a mixed population of stars in our J-region luminosity function. Now, in the Rapocci 2020 paper, they had a plot where they took stars from the carbon star catalog from LaMost that has spectroscopically identified these J and N-type carbon stars. They plotted a color magnitude diagram, and they found that these J-type and N-type carbon stars lie within the J region. So that's within the color cuts, the vertical cuts of 1.4 to 2. Now, what we did was we took stars from the Avia 2022 paper, and which had also spectroscopically identified these J and N-type stars. And we applied color cuts to make sure to extract the stars that are in the J region, and then we plotted their luminosity function, or essentially the histograms of their magnitudes. And what we found was that there's two distinct luminosity functions created by these N-type and J-type stars. In particular, the mean of these two luminosity functions are actually not really consistent with each other. Now, one point to note is that these J-type carbon stars are extrinsic carbon stars, meaning they get their carbon from a companion star. That also means that their mass range is not necessarily restricted by the traditional argument for intrinsic stars, that if you're too heavy or too massive, Bonham burning will occur. If you don't have enough mass, the drive-up events aren't efficient enough. And qualitatively, we can see this in the histograms and the luminosity functions, where the luminosity function for the J-type is less symmetric, and there's a wider range of luminosities. Whereas for the N-types, the luminosity function is much more symmetric and well-defined. So I wanted to make one more note about this asymmetry. It's more of, the effect of asymmetry on the measurements. And so the mode-based method involves a smoothing parameter. Again, you can control the degree of smoothing in that measurement. And when you have an asymmetric luminosity function, by nature, the Gaussian smoothing will try to reduce that asymmetry. And that means that when you have an asymmetric luminosity function, changing the smoothing parameter, the strength of the smoothing will also shift your mode. And that's what we show here on the right, where we have an asymmetric luminosity function from NGC 4258. And then when we use different smoothing parameters and increase the level of smoothing, we see that that pushes the mode of the luminosity function towards the right. And so that's an additional consideration. When you look at the methodological variations, of course, when you have an asymmetric luminosity function, there's going to be a difference between your mode and your mean and your median. But even within the mode-based measurements, there can be this variation due to your choice of smoothing. And so now I wanted to start wrapping up and talk about some future directions. And so to lead into this, we do find broad agreement again with the Cepheid distances. When we plot here on the right-hand side are the distances, JAGB distances from our program in blue, plotted against the Cepheid distances on the x-axis. They also include the Cepheid versus JHB comparison from the Zagorski paper. And we do see that for the blue points, they're pretty consistent with the Cepheid variables. Now, that said, the Zagorski paper found an outlier in their analysis in N4247, and that corresponds to the point way down here. And so in their analysis, they excluded that measurement as an outlier. But a good question to consider is if we do find an outlier in future JWST data, what are grounds for excluding any? Do we include the full sample, or do we, simply throw out galaxies when we measure H0? And that's something to keep in mind in the future. Now, another question is how far can we extend the JHB Cepheid comparison? So again, fortunately, the JHB is brighter than the TRGB. And so we do have an observation of NGC 5468, which lies at roughly 40 megaparsecs. This galaxy is far enough that the I-band TRGB cannot reach that far. There's also NGC 3147, which is also about roughly 40 megaparsecs. So it'll be interesting to look at that and see if we can extend the JGB distance scale that far. Now, there's also incoming data from Cycle 2 Program 2875, led by Adam Rees. And by the end of that program, we'll have essentially double the number of supernova host galaxies that we can use to measure a JHB H0 width. Now, there's also another great program led by Professor Friedman, JWST 1995. It'll observe 9 additional host galaxies that are not observed in the first 2 programs that I described, so 1685 and 2875. They have published a preliminary analysis of some of their galaxies, and that's shown, I'm showing their color magnitude diagrams on the right here, so I encourage you to look at that. That's led by Abby Lee. And what will be interesting is that both 1995 and 1685 had observed NTC 5643. And so it'll be very interesting to compare the results, both JGB and Cepheids, from those 2 independent programs. Now, another thing that will be very interesting to look at is the field-to-field variation in the JGB. Now, at the moment, of course, because, the method is fairly new and JWST is fairly new, there are very few JGB fields in galaxies that have been observed with JWST. Now, what will be very important is once we have more observations and more fields and more galaxies, it would be great to characterize the field-to-field variations using that increased sample of fields. And this would be similar to what the comparative analysis of TRGBs or the CATS team did for the TRGB. What they did was they took many, many fields observed by the Hubble Space Telescope in both NGC 4258. So that's what I'm showing here on the right-hand side. They had 10 different fields, as well as galaxies from the GHOST survey. And they measured the TRGB in all of these different fields, noticed that there's variations in those fields, and then kind of came up with something called a contrast ratio to better standardize the TRGB in light of those field-to-field variations. And so again, it'll be very important to maybe do something similar with the JAGB, really see to what extent field-to-field variation exists in this standard. And the Roman Space Telescope, as well as more JWST observations, will certainly help characterize this. So now wrapping things up, in this study, we did investigate the standardization and the consistency of the JAGB using JWST. We did find evidence of field-to-field variations in the JAGB magnitude, as well as non-uniform asymmetry in the J-region luminosity function, which inevitably causes differences in the measured JHB reference magnitudes, which also mean differences in the distances and H0 measurements due to your choice of method. Now, we do see broad agreements with Cepheids, TRGB, and Miras, but because there is this methodological variation, and because it's so large, we would argue that these variations really need to be accounted for in the error budgets of your measurements, which is what we do here, or ideally somehow standardized in the future, which may be possible with more JWST observations and Roman coming online. Now, a word of caution is that for the study we presented here, we're really working with only a very small subsample of host galaxies. So we only have 4 galaxies, as well as 1 anchor galaxy, and that's NGC 4258. And so we do find a median H0s out of all our variants of 74.7. And that agrees very well with the Cepheid H0s. But the full range, there is a full range of 71 to 78 that really depends on which method you choose. And so all in all, I think the JHB does seem to be a very promising standard candle. However, there's still a lot that we don't know about and still a lot of work that needs to be done. But I think that's perfectly natural given how new this method is. And so I certainly look forward to future missions such as Roman and also more JWST observations that'll really help us better characterize and standardize the JGB so that it can be more competitive with other more established standard candles such as Cepheids and the tip of the red giant branch. So I'd like to thank you for your attention, and I can start taking questions.
Thank you so much. Thank you, Sean, for the very nice talk. Any questions? So,
Yeah.
Laura?
Thank you, Sean, for the great talk. I was wondering because in your outlook, you mentioned that you look forward to standardize the JAGB better.
Mm-hmm.
So do you have any idea how to do that? Like, could you, for example, look at the fields and throw away the ones that have asymmetric luminosity functions and just choose the ones that are more symmetric?
Yeah, that's a really great question. Thanks for asking that. Yeah, so one way that I could potentially be used to better standardize this is first kind of isolating the populations. And so if it could be, so I mentioned that there might be mixed populations in the J region that we're looking at. And so one way to improve the standardization could be to clean the sample up. If there is a way that we can exclude or identify the J-type carbon stars and really isolate this N-type carbon star luminosity function, that might really improve that standardization. Another way is, yes, so you mentioned like the asymmetry. And so what the Prada paper does and what they propose is that because this asymmetry can be linked to potentially the metallicity, what they do is they take these, the LMC-like luminosity functions, which means that they take the asymmetric luminosity functions and use the LMC to calibrate those, and then take the more symmetric luminosity functions and then use the SMC to calibrate those. And so that's the idea, that you're trying to use similar populations in both your anchor and your host galaxies. Now, that could be one potential way, but I think there definitely needs to be more work done. Definitely here we only have two different galaxies, 6822 and 1613. The question is, what if you have a luminosity function that has an asymmetry that's in between the LMC and SMC? And so that would be an issue. And so before, throwing out galaxies or like matching these galaxies, it's still really important to increase the sample size and better understand this metallicity effects. Did that answer your question?
Yes, thank you.
Yeah, Wendy?
I just want to comment, I thought that was a very nice presentation, Siyang, and you put a lot of work now into trying to understand differences and how to fit. I think one point to be made, though, is you really do, in fitting other galaxies, want to standardize whatever method you choose. So if you're using the mode in one case, you're going to use the mode in the other case, and then you get away from the many of the wide variations that you're seeing. And you are seeing good agreement, it looks like, with the Cepheid distances, and we find the same when we look at JAGB stars and our program Galaxies. But it's really excellent agreement at the 2% and sometimes better level with the TRGB. So I think it's important to standard. You can't simply say, okay, if you use the mean, you're going to get a very different answer, and you're not going to use the mean in one galaxy and the mode in a host. So you want to compare apples to apples, and you do that with Cepheids also, right? You can change various parameters, and you see that there's a range, but once you standardize your method, fix the slope of your period luminosity relation, for example, then you apply the same to all galaxies. That's, of course, what you want to be doing. So I just want to comment on that. And I think your first point about the J region, the JAGB name. So when Barry and I named the JAGB method, it was, in a sense, just analogous in some way to TRGB. But the J region that was identified by Nikolaev and Weinberg, they had done their plot, as you know, as K versus J minus K, and there's a slope to the JAGB stars. And we recognize that if you did it in the J band, that of course takes out the slope, and then you don't have to do any correction. And so both applied. It's best applied in the J band because you don't have to worry about the slope, and it's in this J region that was named by Nikolaev and Weinberg. But anyways, that's just a historical point of how the name came to be. But as you know, you can correct for a color slope, and so you can choose other wavelengths, of course.
Great, thank you for your comment.
So let's thank Sean again.
Thank you.
Bye-bye, have a nice week.
Bye, everyone.